All right, thermal expansion example problems. First problem, I have a volume V of a substance with a linear expansion coefficient alpha. I heat it up by an amount delta T. What is its volume now? Well, as you recall, our equation is the change in volume is just equal to the volume expansion coefficient times the original volume times delta T, right? And we had reasons in our presentations why it should be linear in temperature change and why it should be linear in the initial volume, and all the rest of the physics is put into this coefficient of volumetric coefficient of expansion. And as you'll recall, for solids we don't usually talk about volume expansion coefficients, we talk about linear expansion coefficients, and the volume coefficient is just 3 times the linear coefficient. So the change in volume is just 3 alpha V delta T. So what's the volume after we heat it up? All right, that volume is then just, the total volume is just going to be, call it V final, the initial volume plus delta V, or V times 1 plus 3 alpha delta T. And there's the answer. Okay, yeah. One thing I wanted to point out, though, that's the problem. It's done, all right? I mean, we can check it. We don't have any numbers to plug in, but we can check it and make sure that the units work out, all right? Linear expansion coefficients have units of inverse temperature times temperature. That's unitless, that's unitless. This is a volume, all right? The volume increases as the temperature increases. All these things we can do to check our answer. But I want to just do an aside here and kind of point out that we're doing a little bit of fudging when we do linear expansion coefficients, as you know we should be, because when we presented them in the video lecture, I discussed kind of we're doing like a Taylor expansion sort of thing. Let me show you how we could have worked this problem. Not the way you would think to work it, but what I could have said is I could have said, let's work this backwards, okay? Let's say I started with the final volume, and let's just pretend like I know it, right? And then I can solve for it in the end. But I have this final volume. I could say, well, the initial volume is just going to be the final volume minus some change in volume, all right? But that change in volume, if we think of it this way, we're starting with the final volume and doing a temperature change, so that would be just minus 3 alpha, the final volume times delta T. So this is how much, if we did the experiment backwards, we start with the VF, lower the temperature, and it shrinks, we should get this back, right? And these two should be reversible. But if we solve this for VF, are we going to get the same thing we had before? So V is equal to, we factor out the VF 1 minus 3 alpha delta T, all right? So I put a minus sign there because I'm assuming delta T is positive. Well, I guess I'm being a little bit confusing, all right? Yeah. Anyway, moving forward, if I solve this for VF, we get V over 1 minus 3 alpha delta T. And you see, it's basically the same problem, right? We just chose to solve it backwards, but we get a different answer. And the point is, right, it kind of illustrates the fact that how does the volume change? Well, we put in the initial volume, but if you break this temperature change up into little pieces, with each little piece of temperature change, the volume that we start with before that, right, we're going to do the temperature change in steps. So maybe delta T is 10 degrees C. What if I took it in 1 degree C steps, all right? In the first step, we'll get some change in volume. In the next step, though, we have to use the new volume to find out how much it expands in the next step. And so we're kind of doing things loose and wild when we use this equation. And as a result, when we do it backwards, we start with a big, right? We plug in the bigger volume here instead of the smaller one, and our temperature and our change ends up having the total final volume rather than the initial volume. All right, so you get different answers, but the point is, in each case, we're already doing some hand waving. We're assuming that the volume change is very small. And when we do that, it turns out that these two are identical. In the limit of this being just a very small thing, if you take a Taylor series of this, you get effectively the same thing as this. All right? So don't let that confuse you. This is a good thing to do, but remember when we derived this stuff, when we sort of hand-waving derived it in the video lecture, our assumption was small changes in volume. And because of that, we were able to get away with it. And because of that, this really is the same thing as that, even though technically, algebraically, they're not. Okay, next problem. A copper plate at 25 degrees C has a hole in it with a diameter of 1 centimeter. A Pyrex rod at 25 degrees C has a diameter of 1.005 centimeters. At what temperature will the glass rod just fit into the hole in the copper plates? We're assuming we're going to heat both of them or cool them both together, all right? And we have these two expansion coefficients, all right? Okay, so we have all the numbers, but as you probably expect, I'm just going to work things algebraically. I'll let you put the numbers in, all right? So what we're given is we're given a copper plate, and it has a hole in it with a diameter dcu. We're given a Pyrex rod with a diameter d Pyrex. We're given the expansion coefficient of copper. We're given the expansion coefficient of Pyrex. We're given an initial temperature, and we want to find a final temperature such that these two diameters are now the same, all right? And so what we're going to do is we're going to say, well, as I heat things up or cool things down, how does the diameter of the copper change? Well, let's call it d copper prime. That's going to be the original diameter of the copper plus how much it changed by, which is alpha copper diameter, initial diameter of the copper times delta T, right? And then we find the final diameter of the Pyrex. I'll call it d prime Pyrex, and it's going to be the original diameter of the Pyrex plus the thermal expansion coefficient of Pyrex times the initial diameter of Pyrex delta T. So here's the change in the diameter. And all we have to do then is we set these two equal to each other. We want to know at what temperature they're equal to each other. All right, so I'm going to set this equal to that. This is a given. These are all givens, and I can just find delta T. And then I can say, oh, my initial temperature is 25 degrees, and I add delta T to that. Now, is delta T going to be positive or negative? We can intuit that, all right? The expansion coefficient of copper is larger than the expansion coefficient of Pyrex. So as I heat them up, the copper is going to expand faster than the Pyrex. I need the copper hole to get bigger, right? The copper is smaller, so as I heat this up, the copper will expand faster than the Pyrex, and eventually I should be able to stick the Pyrex rod into the hole. All right, so we expect, just looking at this, that the temperature change we need should be positive. So if I work this out, if I solve this and do the algebra and find my delta T, and say T final is just T initial plus delta T, if delta T ends up being negative, I probably did something wrong, right? That's something I can check. Okay, I think you can do the algebra, so I'm not going to work this problem any further. A final problem. A scuba tank is designed to be pressurized to 200 atmospheres. Its specifications say that it holds 100 cubic feet of air. What is the actual volume of the tank in cubic feet? All right, the tank isn't, I mean, 100 cubic feet of air is huge, right? The scuba tank couldn't really be 100 cubic feet in volume. Well, what it's saying is basically, I can pressurize it to 200 atmospheres. If I take all of the gas that's in that tank when I pressurize it to 200 atmospheres, and I let it expand at constant temperature until it was at atmospheric pressure, then it would fill 100 cubic feet. All right? So, how do I find what the actual volume of the tank is? Well, the point is, inside the tank, I've got a pressure, PV equals nRT, right? So I'll call this the pressure in the tank, volume in the tank is nRT, and we're going to let T be atmospheric pressure, or sorry, room temperature, all right? So in the tank, this is true, but then we let it expand at constant temperature into the air, and we're going to get the pressure in the air as atmospheric pressure. I'll call this the volume in the air, and that's going to equal nRT, right? So the number of molecules is the same, the ideal gas constant is the same, and we're assuming that the temperature is the same. So I have this high pressure gas in the volume of the tank, and I will let it expand to this. Since these two are equal, right? Number of molecules is the same, the temperature is the same before and after we let the air out of the tank. All right, we can set these two equal. So the pressure in the tank, the volume of the tank, is equal to atmospheric pressure, volume in air. And the volume in air is 100 cubic feet. So this is 100 cubic feet right there. That's 1 atmosphere. We're given this right here. The pressure in the tank is 200 atmospheres. What's the volume of the tank? So we just have to solve this. So the volume of the tank is just P naught VA divided by VT. All right, and P naught is 1 atmosphere. The volume in the tank, is, or the volume once we expand it into air, is 100 cubic feet. All right, and then we divide by the volume. Solved that wrong, didn't I? So my volume in the tank, this should be the pressure in the tank. The pressure in the tank is 200 atmospheres. Okay, now expand it out to 1 atmosphere. That's absolute pressure, right? Gauge pressure of 0. Kind of putting it out to the average. When it says the tank can be pressurized to 200 atmospheres, probably they're telling us the gauge pressure, what the gauge on my tank would read, which means that the absolute pressure in the tank is actually 201 atmospheres. So probably to get the right answer, I need to put in 201 atmospheres. That makes it harder to do this calculation in my head. Otherwise, right, I could just cancel the atmospheres, and 100 over 200 is just 1/2. All right, so this is about 0.5 cubic feet. But because this is really probably supposed to be 201 instead of 200, to get this out to so many decimals of precision, I should probably do it on a calculator. And there you have it. Those are the problems.